And today I will give two talks. Both of them will discuss how to incorporate the 3D point source in our SS procedures. The first talk, I will show you the significance of incorporating a 3D point source in our SS free surface multiple elimination algorithm for a 1D subsurface. This is the seismic processing train provided by the M-OSRP, and we can see that the free surface multiple elimination algorithm here requires the data requires the reference wave removed and the ghosted data, which has been discussed extended to a complex elastic case by my colleague Xinglu in her presentation yesterday. And my colleague Dr. Xinglu just showed you the impact of residues of ghosts in the data on these resurface multiple prediction algorithm. In my talk, I will focus on incorporate a 3D point source in this SS resurface multiple elimination algorithm, and then continue on this work. We will examine the resurface multiple residues in the data will have what kind of impact on the subsequent internal multiple attenuation algorithm. So here is the outline of my talk. First, I will go over the motivation of this object and this subject, and I will briefly give you an introduction of the 2D line source, 1D Earth, and the new 3D point source, 1D Earth, as resurface multiple elimination algorithm. After that, I will show you two numerical examples. For each of them, we will examine the isolated tasks. And finally, I will give the conclusions. First, let's take a look at the motivation. In multiple removal tasks, as we have mentioned before by my colleague, Dr. Xinglu Yang, people usually use the adaptive subtraction to eliminate the multiples with the energy minimization criteria. However, energy minimization criteria can fail when the primaries and multiples are close or interfering with each other. Our SS free surface multiple elimination algorithm can provide you both the accurate time and the amplitude of the free surface multiple prediction. And when the Earth is 1D is close to 1D, which is reasonable for many circumstances, the 2D line source 1D Earth algorithm has been developed by our group, M-OSRP, and widely used by our sponsors. Well, if we consider the source dimension in the real data is a 3D point source, which means it's a local source like a dynamite. If you directly apply this algorithm, assuming 2D line source on your data, which means you mismatch the source dimension in your algorithm and in your data, you will have issues. This project will focus on incorporating a 3D point source in the 1D Earth free surface multiple elimination algorithm. And we will start from a complete 3D theory, reduce the Earth from 3D to 1D. And which means our reduced algorithm will remain the 3D point source assumption. That will make the algorithm more effective and realistic. We would like to emphasize two main points in this talk at the beginning. The first is, in this talk, we will compare the SS free surface multiple elimination predictions in the algorithm assuming a 2D line source versus a 3D point source for 3D point source data. The second is, we will examine the issues generated by the free surface multiple residues in the data in the subsequent SS internal multiple attenuation algorithm. Let me briefly introduce the data requirement of the 2D line source algorithm and the new 3D point source algorithm for the free surface multiple removal task. Let's first take a look in this 2D world. Here, I use the green spots to represent the source locations and the red spots to represent the receiver locations. The complete 2D algorithm requires a line coverage of all the receivers for each shot, and also we need the sources to be everywhere along this 2D line, which means we need the line coverage of both the sources and the receivers to do this Fourier transform as our input data. If your Earth is not 2D, it certainly tends to be 1D, you will see that the data is independent of the source location, which means this kind of symmetry can allow us to reduce this data requirement from a 2D line acquisition to only one shot gather, like the picture shows here. So now our algorithm for a 1D Earth, assuming a 2D line source, can work on one shot gather at a time. And please let me remind you that we start from a 2D line source algorithm. So this reduced algorithm still retains the 2D line source. If we want to incorporate the 3D point source in our algorithm, we need to start from a 3D theory. So in the original 3D source, 3D Earth free surface multiple elimination algorithm, we need the data, we need all the area coverage of other receivers for each shot, and the area coverage of the sources on the same area, which means we need an area coverage of both the sources and the receivers. And what if the Earth is 1D? If the Earth is 1D, it's a 1D Earth, the data doesn't care where is your source, which means it's independent of the source location. That allows us to reduce the data requirement from an area coverage of the sources to only one shot. Okay, about here. Well, in this case, you still need an area coverage of the receivers, but if we further put this receiver geometry in a cylindrical coordinates, you will find that the data is independent of this azimuth angle, which means it only cares about the outside along this R direction, which can be represented by this RH here. So that we reduce the complete 3D algorithm for 1D Earth to make it work on one shot gather at a time. Okay. Please let me remind you that since in this case we start from a 3D algorithm, that 3D point source assumption remains in this reduced algorithm. Let me give a chart to compare these two different source dimension assumption algorithm. In this first column is the workflow to implement this 3D source 1D Earth as resurface multiple algorithm. And in the second column here, we give you the workflow for the 2D line source, widely used 2D line source 1D Earth as resurface multiple elimination algorithm. In the next, we will show you what kind of difference can these two algorithms make for a 3D point source data. The first, I will give two numerical results. The first numerical results in this model 1, we will examine the significance of incorporating a 3D point source for 3D point source data. In this model, we generate the synthetic data with this model using reflectivity method. And please notice that the source dimension, the source is a 3D point source here. And you will see our data here only contains two primaries and two free surface multiples without ghost and the reference wave, which means this data set satisfies the prerequisites of free surface multiple elimination algorithm. If we use this data as the input of our free surface multiple prediction, and first let's look at the result from the 3D point source as free surface multiple algorithm, which means we match the source dimension in our algorithm and the source dimension in the data. We will have the result shown in the right panel here. And the left panel which shows the original input data. We plot these two figures in the same scale. So you can see that the prediction of free surface multiples have the same amplitude scale as the original data. If we arbitrarily pick up one trace to do the trace comparison, I use this solid blue line here to represent the original free surface multiples in the original data, in the 3D data, 3D point source data. And then we plot a 3D point source as free surface multiple prediction on the same plot. You will see, using this red color line, you will see this line is completely overlapped with the original data. We can flip back and forth. You can't see any difference. So that means when we match the source dimension in the algorithm and the data, we will have, our algorithm will give us both the accurate time and the amplitude of the prediction. If you use this kind of prediction to do the subtraction, you will see that your free surface multiples will be completely removed. Next, let's take a look. What if we apply a 2D line source free surface multiple attenuation algorithm on our 3D point source data, which means we mismatch the source dimension in the algorithm and the data. What will we get? Okay, we get the prediction shown in the right panel here. Please notice that to make this result visible, we use a different scale for these two figures. You can see that here, the prediction result contains a very small amplitude and compared to the original data. If we plot them in the same scale, you can barely see any prediction in this result if you mismatch this source dimension. Let's arbitrarily pick up one trace to do the trace comparison. And again, this blue solid line represents the original 3D point source data. We plot this 2D line source prediction on the same plot. You can see that this prediction gives us very small amplitude and also phase shift, which means when you mismatch the source dimension in your algorithm and in your data, you will have significantly less effective prediction on both the amplitude and the phase. If you use this kind of prediction to do the subtraction, you will have free surface multiple residues in your data. Next, we continue on this task, but in this task, we will focus on examining the impact of the free surface multiple residues on the subsequent SS internal multiple attenuation. Our SS internal multiple attenuation algorithm assumes that all the free surface multiples in your data set needs to be completely removed. Here is the model we use to generate this synthetic data. For more easier to observe, we use the density variation only model here. And this data set contains 2 parameters, 3 free surface multiple events, and 1 internal multiple. We can see this is the data we got, the 3D point source data. If we set up 2 different experiment sets, In the first one, we match the source dimension in the free surface prediction, and the other one, we mismatch it. To be fair, for both of them, we use the data satisfies the prerequisites, which means without reference wave and ghost. And then we do the different source dimension free surface multiple prediction, subtract it, and then continually we will do the 3D point source SS internal multiple attenuation algorithm on both of them. So follow the first experiment step, which match the source dimension in the free surface prediction algorithm, and the source dimension in the data. We will have the result here. We can see that, flip back and forth. We can see that all the free surface multiples have been completely removed. We only have 2 primaries and 1 internal multiple. This kind of data satisfies the prerequisites of the internal multiple prediction. So that if we use this kind of output as the input of the subsequent SS internal multiple prediction, we will have the result on the right panel here. On the left panel is the free surface multiple removed result without any free surface multiple residual. And on the right panel here is the internal multiple prediction result, B3. We can say that B3 provide us an accurate time of the internal multiple and approximate amplitude here, which is pointed by this yellow arrow. In the next test, let's mismatch these source dimensions in this SS free surface multiple algorithm. We will get the result shown here. Let's flip back and forth. This is the 3D data as the input. This is the mismatched 2D line source free surface multiple removed result. We can see the problem of the free surface residues is very serious. Okay? So if we use this kind of data as the input of the subsequent internal multiple prediction, you will have the result on the right panel. You can see all the residuals. You can see that if we use this kind of data as the input of the internal multiple prediction, you will have the result shown here. Because you did not satisfy the prerequisites of the internal multiple prediction, so in this result, in this B3 prediction, we have a lot of artifacts. And then we can catalog them into 3 kinds. The first kind is the force events, which means this kind of events in the prediction does not exist in your original data. The second kind here is the events located on the free surface multiple residues. In this specific case, if you subtract the right panel from the left panel here, you will enlarge the free surface multiple residues. And the third kind is the worst thing, which is located on the internal multiple prediction, which means that this kind of artifacts can over-enlarge this internal multiple prediction, which makes it no longer a attenuator. So let's draw the conclusion. Here are 2 key points we would like you to take away from this presentation. The first is the 3D point source 1D subsurface free surface multiple elimination algorithm works on one shot gather at a time and accurately predict both the time and the amplitude of the free surface multiples. Applying a 2D line source SS free surface multiple elimination algorithm, which is widely used now, on this 3D source data can generate significantly less effective free surface multiple predictions for both amplitude and phase. The second key point is the residues of the free surface multiples in your data generated by applying the mismatched source dimension in the free surface prediction, can produce artifacts in the subsequent assets internal multiple attenuation algorithm, which are false events not existing in your original data, and the events located on the free surface residuals, and also the events located on the internal multiple prediction. So this study is part of the broad strategy of meeting the prerequisites. And the results here tell us that any step or prerequisites cannot be provided will lead to harmful consequences in the subsequent processing. At the final, I would like to thank all the sponsors for their all-time support and encouragement, and any questions are welcome. Thank you.